We use AI literally every single day. And let's be real, sometimes it feels like straight up magic. But it's not. And today, we're going to pull back that curtain. We're going to look at the incredible engineering that makes it all tick. So let's dive right in. First up, think about this machines that can see. How do you even teach a machine to do that? I mean, we've got cars now that can navigate a crazy busy street, right? They're spotting pedestrians, other cars, traffic lights, all in real time. This is way more than just a camera recording something. It's a system that's actually perceiving and understanding what's around it. And that right there is the power of computer vision. And it's not just about seeing, is it? It's also about listening. Every time you ask your smart speaker to play your favorite song, well, that's not magic either. It's this super sophisticated speech recognition that takes the actual vibrations of your voice and turns them into a command that a machine can actually act on. Pretty wild. But, understanding is so much more than just hearing words. Now, machines can process, interpret, and even translate human language. I mean, think about it for a second. A tool like Google Translate can take a whole sentence in one language and, poof, almost instantly, it gives you a totally coherent translation in another. That is just an incredible feat of what we call natural language processing. So, seeing, listening, understanding, these are things we think of as deeply human, right? So the big question is, how on earth did we manage to teach a machine, which is really just a bunch of circuits and code, to do all these things that feel so magical? Well, that's the mystery we're going to solve today. All right, let's kick things off with sight. How do you give a machine eyes? Well, the answer lies in this amazing field called computer vision, and the most powerful tool in its toolbox is this absolutely brilliant piece of engineering called the convolutional neural network. So, what is computer vision? At its heart, it's all about teaching a machine to make sense of what's in a picture or a video. And the engine that drives all of this is the convolutional neural network, or as you'll often hear it called, a CNN. Now, what a CNN really is at its core is a pattern detector. It's built to scan every single pixel in an image and learn to recognize everything from the simplest things, like an edge, to really complex stuff like a human face or a car. And this really gets to the core idea of how a CNN works. It's a process called convolution. I want you to imagine sliding a tiny little stencil, we call it a filter, over a photograph. Now, this stencil is designed to light up, to get excited, whenever it finds a specific pattern it's looking for, like a straight edge or a gentle curve. The network then uses thousands, and I mean thousands, of these little stencils to build up a super detailed map of all the features in the entire picture. Okay, so after the network finds all these different features, it has a ton of information. It needs a way to kind of summarize it. And that's where something called pooling comes into play. It's a bit like looking at a small grid of pixels and just picking out the single most important one to keep. This does two really cool things. First, it makes the whole system way more efficient. And second, it actually helps the network recognize an object even if it's a little off-center in the picture. Super clever. And this stuff isn't just theory, it's everywhere in the real world. Think about it: Tesla's autopilot identifying a pedestrian, or a medical AI that's helping a doctor spot a tiny tumor on a scan. Even something as simple as unlocking your phone with your face. Yep, all of that is powered by these very ideas: CNNs, convolution, and pooling. Okay, so we've got machines that can see static images. That's awesome, but what about something that unfolds over time, like a sentence or music? That brings us to our next big challenge. How do we teach machines to understand sequences? And this is a totally different ballgame, right? With an image, all the pixels are just there, all at once. But in a sentence, the order of the words is everything. The dog chased the cat means something completely different from the cat chased the dog. The meaning depends entirely on what came before, and sometimes even what comes after. So how in the world does a machine keep track of all that context? The answer is a whole different kind of architecture. It's called a recurrent neural network, or an RNN. And the key innovation here, the really clever part, is a loop. See, an RNN processes a sentence one word at a time, and at every single step, it passes along a little bit of memory of what it's already seen to the very next step. This constantly evolving memory, it has a fancy name, the hidden state, is exactly how it hangs on to context. But a standard RNN has one big limitation. It's kind of like trying to read a book, but only ever being allowed to look at the words that came before. You're missing half the story. To get the full picture, you need to know what's coming up too. And that's exactly why engineers came up with the bidirectional RNN. It's basically two RNNs working together. One reads the sentence forwards from start to finish, and the other one reads it backwards from finish to start. Put them together, and the model gets a complete 360-degree understanding of the context. Now, those basic RNNs still have a problem. Their memory is, well, it's pretty short. They really struggle to connect words that are far apart in a long sentence. The solution? It's called a long short-term memory network, or LSTM for short. The best way to think about it is like an RNN with a superpowered memory system. It has this memory conveyor belt and a series of gates that let it intelligently decide what information is important enough to keep and what it can afford to forget. This lets it track context over much, much longer sentences. So, once you have these models that are great at handling long sequences, what can you build with them? Well, how about a translator? This is where we combine two RNNs into a really powerful setup called an encoder-decoder model. Here's how it works. First, the encoder RNN reads the entire sentence you give it, let's say in English, and it squishes the whole meaning down into a single list of numbers. Some people call this a thought vector. Then, the second part, the decoder RNN, takes that thought vector and uses it as a guide to start generating the translated sentence, maybe in French, one word at a time. It's like one part understands and the other part speaks. All right, so we've got these incredible, really clever models, but here's the thing. How do we actually make them run efficiently on your phone or in your car without, draining the battery in 5 seconds flat? That's where the real nitty-gritty engineering comes in. Exactly. I mean, a model is pretty useless if it's not fast and reliable, right? So how do the engineers actually tune these super complex systems to get the absolute best performance without making you wait hours and hours for a single result? A huge, huge part of the answer is something called hyperparameter tuning. The easiest way to think about these are the knobs and dials on the outside of the machine. The model learns all its own internal settings during training, but it's up to us, the engineers, to set these external parameters. Things like how fast should the model learn, or how many layers should it have? Finding that perfect sweet spot, that perfect combination of settings, is the absolute key to unlocking a model's true power. And there are a few different ways to find those perfect settings. You could use grid search, which is the brute force method. It literally tries every single possible combination, and yeah, it takes forever. A little better is random search, where you just try a bunch of random combinations, but the smartest approach is called Bayesian optimization. This is really cool. It actually builds a little model of the settings, and it learns from every attempt it makes. So it gets smarter over time, making educated guesses about where the best settings are likely to be. This makes the whole search process way, way faster. It's not just about tuning, though. Engineers also optimize the core math operations themselves. Remember that stencil thing we talked about, convolution? Well, doing it the straightforward, standard way can be pretty slow. So for specific situations, we use really clever algorithms. For big stencils or filters, there's one based on something called FFT. And for the super common 3x3 filters, there's an algorithm called Winograd that is just incredibly fast. It's these kinds of speed-ups that make real-time computer vision, like in a self-driving car, even possible. Okay, let's take a step back and pull all these different threads together. We started out by talking about the illusion of magic, but now we've actually seen the machine behind the curtain. So what we've really uncovered here isn't one single magic bullet. It's more like a brilliant toolkit, full of specialized components for different jobs. We've got CNNs, which are perfect for processing spatial data like images. We have RNNs and LSTMs to handle things that happen in order, like language. We've got architectures like the encoder-decoder that can translate from one world to another. And then we have this whole collection of optimization tricks to make the whole shebang run fast and efficiently. And really, that brings us to the end. We started with things that looked just like magic, and now we've uncovered the clever mechanics and the incredible engineering that makes it all possible. It's this powerful combination of ideas that has already fundamentally changed our world. So the only real question left is, now that we've built machines that can see and speak, what should we teach them to do next?